Welcome to Pomodoro Joe for Wednesday, August 16th, 2023. Today we're looking at LeetCode problem 239, sliding window maximum. This is a hard problem. What? Hard problem on a Wednesday? What the? Alright, so you are given an array of integers, nums. There is a sliding window of size k, which is moving from the very left of the array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position. Return the max sliding window. Okay, so this doesn't make a whole lot of sense to me. So let's take a look at the example. To me, when it says the max sliding window, does that mean the maximum sum? The window with the highest maximum sum? I'm not really sure what this means. So let's take a look at this example. So the input, we have some nums array, and then we have k equals 3. All right, so the window position in the very beginning, it will have the first three elements. So that's 1, 3, negative 1. So that's a sum of 3. Okay, has a max of 3. Then it has 3, negative 1, negative 3. So that would be a sum of negative 1, but it looks like you have max 3. So it looks like this is actually the maximum value within the window. So the max single element within the first window is 3. The max single element within the second window is 3. All right. And then the third window, the max is 5. Okay, so this is looking for the maximum element within the window. 6 and then 7. And we return, I see, so we return an array. So for each window, what is the maximum element in that window? And then we return the array of all the maximum elements of all the windows. So each entry in this output represents one window, and this value represents the maximum value within that window. All right, so this is confusing based on the wording, but I get it now. Okay, so let's do this super simply, and this is probably not going to work because this is a hard problem. A simple solution generally isn't going to work. So the simple solution is, let's just go through the window. We'll just go through every possible window, sliding from left to right, and we'll just call the max function on that window. Super simple. So let's do that. All right, so we'll have to keep track of some left index, and that's 0, and then some right index, and that will start at k. So that's our very first window, and we'll be sliding our window, so we'll also need some result here. Let me put that first, actually. Result is going to be an empty list to start with. All right, so while our right is less than or equal to, or less than, I think it might be less than or equal to the length of our nums. We'll essentially just find the maximum value within this window. So in this case, our max value, well, that's just going to be, we'll call max on nums, and we're going to go from our left to our right. And now this is exclusive, meaning it does not include this element at the right. So that means we can go all the way to the length of our nums and not worry about having an out of bounds exception here. All right, so we'll get the maximum for the nums between our left and right, which is our window. And then we'll just put that maximum value in our result. And then we do need to advance both our pointers. So our left plus equals 1 and our right plus equals 1. And at the very end, we can return our result. I'm tired today. Okay. So that's the straightforward way of doing this. Let's see if this will work. Okay, so this works, surprisingly. But we'll submit this and see if we can pass all the tests. I don't think it will, but we'll try it. And we get a time limit exceeded. We do pass 37 out of 51 though, so it's not too bad. Let's grab this test case. Say no thank you, and now let's get down to the real problem. So before we get started there, I'll put 25 minutes on the Pomodoro timer, and now we will get started. So as we can see, this is a valid solution in terms of it does the right thing, but it's just too slow. And that's because we are calling this max function on every single window. Now, we already know as we move our window along, a lot of these elements will be the same between two windows. Basically, we only drop one element out and add one new element in for every time we slide that window. So this max is doing a lot of redundant work. We'd like to minimize the amount of work that we do. So let's see if we can come up with a better solution. So for this, I'll point out a couple things. So let's just say we have some set of numbers. I don't know, 1, 2, 3, 10, 9, 8, something like this. So let's say this is our number. And if we're looking at windows, well, let's go to 7. Okay. So I don't know what size of window we're looking at. Let's say it's size 3. It doesn't really matter. But when we have a window that includes 10, this 10, for example, let's look at, say, this window. So we know that this 10 is going to be the largest value in this window. We also know that these values that come before will never be the largest value because this 10 will always be in the window longer than this 2 and 3. Because we're moving the window to the right, this 10 will dominate and this 2 and 3 will never be the largest values. Now, as we move this to the right, this 9 could become the largest value because 10 might drop out of the window. So once we find a large value, we can essentially ignore everything that came before it. But as we move our window along, we need to keep track of what comes after it in case that large value drops out of our window. Okay, so that kind of sounds like maybe a heap. So if we had a heap, we would keep track of what's in the window, what's the largest value in that window. When it drops out, we would have the next largest values already in our heap, ready to come to the surface. So that's one way we could try this. So maybe let's try that and see how it goes. I'm not 100% convinced that that will beat the time constraints, but it's worth a shot. So let's try that. All right, let's do this. So we'll have some heap. Now, our heap will have to keep track of not just the value, but also the index, because we need to know when our value drops out of our window. So we'll know that by the index. So this will keep track of our value and our index. And in fact, because we want this to be a maximum heap, we'll have the negative value and the index. Okay. So the first thing we need to do is build up our very first heap. So for I in range, and we'll just go to K. We'll do a heap Q, heap push. So we'll be pushing this value onto our heap. We'll pass in the heap, and then we'll also pass in, and this will be our negative value, so that's negative nums at this index, and then we need the index itself. All right. So this builds up our very first heap, our very first windows. Now we need to go through and essentially add new values to our heap and remove old values from the heap. Now the heap, we don't necessarily need to remove all old values. We only need to remove old values that are at the top of the heap. So our heap might actually grow quite big. This could be a memory problem. But let's go through and find out if it ends up being a problem. Okay, so we still need to go through the right. Now, because we're not using this range anymore, or this slicing, we actually can't go past this length nums, or up to this length nums, so we actually need to drop that down to right is less than the length of nums. All right. So, first thing we'll do, we'll find our current maximum. So, max value, or this is like the max element, I guess. And that will be at the top of the heap, so that's heap at index 0. Now we have to make sure that this is still within our window. So we need to make sure that this index in this max element is greater than or equal to our current left value. So if max element, this will be index 1 of the max element, because that's our index here. So as long as this is greater than or equal to our left, we're still within our window, and we can add this to our result. So let's grab our result here. And now we have to add our element at this right value. So this will grab the very first window, find its max value. Next, we need to add the element at the right. So let's add the element at the right. All right, so we're pushing this new element, which is going to be the number at the right and the right index. Okay, now we didn't cover the pop case. Now if this max element at index 1, so the max element's index, is less than our left, we need to pop that. So in fact, this isn't just an if, this should be a while. We need to keep popping. So let's do that. While the max element at index 1 is less than the left, we'll just pop elements out of the heap. Okay. And now we can grab the element at the top of the heap. So let's get this max element again. So this is some ugly code. Let me redo this. So let's just look at heap. The top of the heap will be at index 0. So let's do this. Heap index 0. So while the heap index 0, element 1, which is its index, well, that's less than left. We have to pop it off the heap. Let's forget this. All right, now we can add the maximum value here. So this will just be heap at index 0, and it will be the 0. All right. Then we need to add our new element, the right element, to our heap. All right. Then we advance our left and right pointers. Okay, let's try this and see if it works. All right, I need to pass in my heap here. Okay, try this. Oh, I need to flip my values around, and it looks like I'm also missing a value. So let's do this. We do want to push this, but we need to flip this around. And it looks like I'm missing the very last one, so maybe I do need to go up to less than or equal to. That doesn't seem right. I think I just need to add one more at the very end. Yeah, I do think I need to do this last one outside of my loop here. So I have to do one last one out here. All right. Okay, so that seems to work. Okay, this was pretty ugly, but it seems to work. Here's the idea. We have a heap. It keeps track of the maximum values within that window. As we go through, we'll add more values onto the heap. We'll check the top of the heap. If the top of the heap has fallen outside of our window, we check its index to see if it's still within our window. If it's fallen outside the window, we need to pop those elements out of the heap. Then we grab the top of the heap, and that will be the maximum value. Okay, so let's submit this and see how we do. Oh, and we get a wrong answer. Why is this? All right, maybe I'm doing this in the wrong order. Maybe I want to grab my first window, add the result first, then we'll go through the rest of the windows. So maybe that's the way to do this. All right, so let's add the result here. Okay, so we'll add our very first result to our result. And then instead of this, we will advance our left and then our right. So while the right is less than nums, we'll advance to left. Then we'll go through, pop things out of the heap that are no longer in the window. All right, then we need to advance to the right. And we'll add this new value into our heap. Let's see. But this was not inclusive, so we've already, we want to add the right first. So our right has already been advanced in this case. So left, we'll pop that out. Now we need to add the right, so that's going to be this one. All right, so at this point, our heap should be in the right state. Then we append our new result. We've already advanced our left, and then we need to advance our right. Okay, and then I don't think I need this one anymore. Let's try this. Okay, well, we have a heap. All right, I need to flip this around. Man, this one is a hard problem. Okay, so now we're working. Let's submit this, see if we can pass. Okay, and we do pass. And we do okay. We don't do great. We beat 59% for runtime and 5% for memory, so not great. Now, I know we only have 5 minutes left, but there is a better way to do this. I just wanted to work through the heap it seems like an intuitive way to do it. There is another way to do this that is more complicated, so I'm going to take a short break, we'll come back, and then we'll jump into the other way of doing this. So here we go. So that is our heap solution to this problem. We go through, we slide our window, we pop elements out of the heap if they're no longer within our window and they would have been the maximum value, and we push new values into our heap as we add them to the right. Now, there are a couple of problems with this solution. The main problem is that our heap is going to continue growing even though many of the elements will no longer be in the window. So we only pop elements out of our heap once they're the maximum value and they are no longer in the window. So there's a whole bunch of elements that are not the maximum value that are no longer in the window, but they're still in our heap. So that's going to be a problem with both memory and runtime. It's taking more memory than it needs to, and when we add new elements to our heap, there's a lot more values in our heap that it has to sort through in order to add this element. So, is there a way that we can keep some of this basic structure, but without all the heap overhead? And there is. So let's jump back and we'll see what we can do. So let's jump back here. And we'll just be modifying our solution to fit this new solution. So we'll put 25 minutes on the Pomodoro timer. Hopefully it won't take that long, but we'll start a new Pomodoro. Okay, so we have our heap solution. We already know that it's not efficient. What can we do to make this more efficient? Well, one thing we can do is use something that's not really a heap, it's not really a queue, it's somewhere in between. So we don't really need to sort all of our values when we put them in the heap. What we really want to do is just keep track of what is our current maximum value, or what is the index of our current maximum value. Then what are the potential future maximum value indices? So if this maximum value falls out of our window, we have our list of potential new maximum values. So as we discussed at the beginning of the video, anything to the left of our maximum value, we can ignore. So once we find a maximum value, that maximum value will be in the window longer than any of the values to its left. And if it's greater than those values, it will also always be greater than those values to its left. But once we find a maximum value, we can ignore anything that came before it. Now, if we move on to a new element to the right of the maximum value, well, that element, it might not be the maximum value now, but at some point our max value will fall out of our window, and this new element to the right may become the max element. So we do need to keep track of the potential future maximum elements. So one way to do that is with again, it's not really a heap, it's something in between. So I'll call it a heap for now, just because we already have this written here and we'll reuse it, but it's not really a heap, and maybe I'll change the name later. So for our purposes, we'll put our maximum index into our heap here. Then when we move to the right, we'll put a new element into our heap. So our heap here will be very similar in that the maximum value element will always be at index 0. But we won't be sorting our heap the way a heap sort works, or the way that a heap will normally sort its elements. We will find some maximum value. We'll put that into our heap. It will be at index 0. Then as we move to the right, we will put more elements into our heap at later indices. So index 1, 2, 3. If we find a value that's greater than something else in our heap, then we can basically remove all of those values that came before it, just as we discussed before. So we find some greater value. Anything that came before that greater value can be ignored. So we can pop those out of our heap, and then we'll put this value onto our heap. So essentially we only need to compare the last value in our heap, the end of our heap, to a new value. If that new value is greater, then we can just pop that value and any other values out of the heap that are smaller than this new value, and then we'll put that new value on. So that will always keep our potential maximum values in this heap without keeping all of the other values that will never be a maximum value. So hopefully that makes sense. Let's just try this. So index of max value at 0. and then all potential future max values. So again, I'm calling it a heap, even though it's not really a heap, and I'm only doing that because I don't want to change all the names and redo all my code here. Well, I guess it's not that bad. Maybe I'll call it something else. Okay, let's call it something else. Let's call it the queue. It's closer to a queue than a heap, so let's do that. Okay, so we will still go through, and instead of just pushing something onto the heap, this is where it becomes a little bit different. We'll just check, is this new value? So if the nums at this index is greater than or equal to whatever's in our queue at the end, that means that anything that came before can be ignored, and we can actually just pop those values out. So this isn't even an if anymore. This becomes a while. So while, let's see, first make sure we have a queue. While I have a queue, and this number is greater than or equal to whatever's at the end of our queue here, we can just pop that thing out of the queue and replace it with this number, because we know that this number is greater and it will be in the window longer. So we can just say queue.pop at -1. And then we do need to add this new number to the end of our queue. So our queue, we will append this new number. And we don't actually keep the number, we're going to keep the index. So this will be append I, and that does mean that when we do this comparison, we have to compare this to nums at the index stored at the end of this queue. All right, I think that covers that. Now let's start our queue off with index 0. So we'll go through our first window here while we have some queue. And the current number that we're looking at, if that's greater than or equal to this number, we know it's going to be in the window longer. We also know it's greater than the number at the end of our queue. So we can ignore that. Anything that came before this number, we can pop out as long as it's less than this number. So we keep popping things out. Then we can append this number to the end of our queue. At the end, instead of this result, we can do append nums at our queue index 0, because index 0 will always store the maximum value, or the index of the maximum value. All right, now down here. Now we're going through sliding our window. I think the first thing we'll fix up is this. So this was popping things out of the heap that are no longer in our window. So we kind of have to do the same thing here. We just need to check, is our current index, our current max index, is that still in the window? And actually, I don't want to slide my window just yet, so let's move this to the end. And let's first check to see, is our current index, our current max index, still within our window? So if our heap, well, let's see, if we have a heap, and it's not a heap anymore, I've changed it to queue, right? So if we have a queue, and that queue at index 0, if this is less than our left, that means it's no longer in the window. We need to pop that out. And in fact, since we haven't moved our left yet, this is less than or equal to our left. We no longer have this, so we have to pop it out. So we'll say queue.pop at index 0. All right, so this is the element that is just leaving our window to the left. Next, we basically do the same thing we did here. Let's just check what's on the right. Actually, I can do all of this. Yeah. So previously, we would go through our heap. We would actually check to see if the top of our heap is still within the window, and we'll pop it out. We're kind of covering that here. And next, we'll push our value onto the heap. So we're going to be doing something similar, but with our right. So instead of nums at index I, this will be our right. So while we have some queue and this num at our current right, so that num that we're adding to our window. So if that's greater than or equal to whatever's at the end of our queue, then we'll pop that out of our queue, and then we will append the right index. And then we do want to add to our result, so we'll just add at our queue. And again, this is the nums. Let me just grab this whole thing. This will be the number at our max index. And then we advance left and right indices. Okay, so hopefully this will make sense. I'm not explaining this very well, but hopefully you can follow along. Let's run this and see how it goes. Okay, and that works. Let's submit this and see if we do better than our heap solution. And it looks like we do a little bit better. So our previous solution was a heap solution with a 59% for runtime and a 5% for memory. This uses this sort of queue solution, a 77% for runtime and a 69% for memory. So it does do better. Now let's jump back and do one slight modification. So right now I'm using a standard list. Now the standard list, while it's great, it's not always efficient when you're pushing and popping elements. Something that works a little bit better for pushing and poppings is something called a deck. That is a double-ended queue. And since we are popping elements out the front and popping elements out the back, this is a double-ended queue. So let's use a deck and use DEQUE, and we'll initialize it with this list. Now it does mean we have to make a few changes here. So the deck doesn't have a pop at -1. Instead it has a pop left and a pop. So we will do a pop wherever we had a pop at -1, and a pop 0 becomes a pop left. Okay. I think that should cover it. Hopefully I didn't miss anything. Let's try that. Okay, let's see if this gives us any type of improvement over our standard list. And it looks like it gives us a great improvement. So now we're at a 95% for runtime and a 20% for memory. So yeah, much improved. Okay, well this one's a little bit long, so I apologize for all my failed attempts to explain, but I hope in the end it makes sense. I'll also post the code. You can check the link in the description. You can see it on GitHub. You can go through it at your leisure, and hopefully it will make sense to you. Okay, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.